Okay, hello. My name is Andrew Martin. I am from Control Plane, and I would like to talk about the provenance and veracity of supply chains and how containers give us a new way to defend against attacks and ensure the continuous flow and the trust in the chain of custody of each line of code that we push towards production. We've got a long time and we're quite a small group, so if you do have anything that you want to ask as we go, feel free to just raise a hand and we'll take some questions in flight. There's quite a lot of new technology in here, so if it's specifically about the technology, hopefully the slides will give you enough to proceed with. So, hello, I'm Andy. I've done a little bit of everything. I'm a build fanatic and ultimately an advocate of continuous everything. I'm a founder at Control Plane, which is continuous infrastructure and security practices with a focus on containerized deployments. And I've done a little bit of everything from databases and architecting to security and penetration testing and development. And I want to talk about the code that we run in production, how it gets there, and how we know it's the same code that we thought we were shipping. So, what is this nebulous supply chain? It's anything that we depend upon. In a military scenario, the origin and transit of all hardware and software has to be attested to, both where it's from and who builds it, to guard against nation-state attacks. And pharmaceutical companies know the provenance of every ingredient that goes into medicine because it's for consumption by humans, and should something go wrong, there are serious, potentially life-threatening implications. And of course, kittens. The supply chain for these kittens is not just the hand that feeds them, it is also the distributors of the frisky bits. It is the warehouse that food was in before it was delivered. The manufacturers, the farmers that fed the chickens, the feed those chickens were fed. So supply chains can be long and difficult to track, with no guarantees of the competency of the upstream providers. Tracking where things came from is even more important. So where does it relate to software? Catastrophe. This is a grossly oversimplified software supply chain. But ultimately, its software supply chain is the travel of any code that ends up in production, and the trusted mechanisms that build, package, and finally deploy that code. Software supply chains can be exploited. We have seen a lot of attacks on them recently. So, bugs in libraries that are depended upon by an application, or deliberate vulnerabilities snuck into dependencies, either in the source code or by compromising the hosting provider upstream, or perhaps by a compromised download through a man-in-the-middle attack, or typo squatting, which is becoming increasingly popular. For example, a library with a hyphen in its name is re-uploaded bit for bit without the hyphen. Developers then go and they make their typos, their mistakes, using the new malicious version of the code, but they don't know it's malicious because it resolves exactly the same package. Then, once they have 100,000 weekly downloads, somebody inserts a backdoor into the malicious version of the package that is pulled automatically by build servers and run inside your estate on your infrastructure. So what can we do then? Well, for example, dumping the environment and posting it off to an endpoint that I control means that I have everything that your build server gives to a build in the context of the build, which may include the keys to your AWS account, or various other useful and expensive things to lose. So when we're talking about supply chain security, we're talking about all of these and probably more. So what have we seen in recent times? The Equifax hack was an example of a vulnerable struts library, and compounded by a vulnerable perimeter-focused deployment strategy, which allowed database access and subsequent exfiltration. Detecting the vulnerable struts library would easily have prevented this attack. These are well-known and published CVEs. So that struts library is in the supply chain for the delivery of that piece of software. Here we had a malicious but legitimately signed version of CC Cleaner, a Windows cleanup tool, and that was delivered to users via their official download servers. So the signing keys were compromised, a malicious binary was uploaded and signed with those keys and then distributed. And a similar attack happened with Clair. A signed malicious binary was distributed. This really is a worst case scenario because it's very difficult to detect, of course. One thing I actually missed from the beginning of this presentation, this is not just my presentation, it is also Mike Wachowski, who is a product security manager at Google Cloud. And my notes just reminded me that this is now her slide. Hi Maya, thank you very much. So, what changes in the supply chain if we use containers? Well, first, we'll look at what happens when we're using VMs and monolithic applications. Historically, that application would run inside a virtual machine, and to make a change, developers would SSH into the machine and mutate some state somewhere, pushing code changes without necessarily being able to predict the impact that would have on the rest of the environment. These were manual adjustments, including things like maintenance operations. We may not ever fully know what was running inside that VM because it is constantly under change, at risk of configuration drift, etc. It's not only hard to debug, but this form of deployment and update is very difficult. There's no formal process around it. So next time we want to change something, we just SSH back into the VM, and we're left with a constantly mutating stream of changes without being able to understand what is there without observing it. That is not a great security story, and it's very difficult on an operations team to lock something like that down. With containers, things are a little bit different. With containers, we can have a pipeline that builds these smaller, immutable artifacts. The main difference here is that by running much smaller containers than VMs, we suddenly have something that's quicker to move around. We have something that takes up less resident memory, and therefore developers are able to use these things on their local machines. The container dream is, of course, what you run on your laptop is what runs in production, because containers are just a bundling and isolation mechanism. It's ultimately just a tarball that's going to production, but with a set of guarantees about the runtime that give us some uniformity between environments. Now, of course, containers share the host's kernel, which means that different kernel versions have different APIs available to containers. They may have different bugs. The networking will always be different because it is contextual based on where else the container is connected to. But these are the major differences that separate the container from the VM. So, rather than changing specific lines of code in a monolith or a monolithically deployed unit of computation, we rebuild the whole thing from scratch every time because it's fast, it's efficient, it's cached, and we can push and pull those container images very quickly. So, this also means that we can put a robust test pipeline in place for our deployments. When we build our images, we can also test them in isolation and as part of a larger system. We can scan them, so CVE scanning is minimum viable security. We should not be shipping CVEs to production because CVEs generally have published attacks and are a very low bar for a script kiddie to drive by and run something against. And then we can QA them, again, all through automation, low touch, high velocity. This doesn't solve everything, of course. It doesn't address dependency management, which remains the same, which is obviously still complicated, and integration testing is difficult, as we know, and must be done correctly. So, going back to the supply chain in general, we'll look at an idealized supply chain broken down into 5 main components that we will focus on for the rest of the talk. We have a base image. This is the from line at the top of a Docker file. This is the container that we pull to start running commands inside to build our final container. It is packaged as part of the final container itself. We have the code. This is what we inject into the container and is our frequently changing and custom changes to the base image. Then we build that, we package it and bundle it together, we pull dependencies, and this is where we're putting in remote things or pushing in things from our local machine. The application image is the result of those preceding 3 steps. This is our immutable deployment artifact. It is content addressable, which means that every layer is hashed, and we refer to each layer by its hash. So barring attacks on SHA-256, it's effectively immutable by reference, by the way that we reference the images, the image layers and the final image. And then finally, we take that immutable image and we deploy it to production by the hash, not using a tag, because tags, like Git, are only pointers to hashes. Therefore, they can change. There have been many attacks against Git tags. There are undoubtedly further attacks against Docker tags as well. So, of course, we should never be running latest anywhere near production. So, unless we've pushed our code through this pipeline, we can't even be sure where it came from, for example. So we'll look at ways to assert that later. So altogether, these make up the components we need to secure the container supply chain. So for each of them, we'll go into best practices and look at what we can do to secure things further with open source tooling. Let's dive in. Of course, I told you I was an advocate of continuous everything. Nothing works without testing. We can just throw stuff at production if we like, but you'll very quickly lose whoever is trying to support that. This is also relevant for security testing. Shift left is the sort of faddish way to describe it, but ultimately running security tests on the developer's local machine, using the container, which is going to run in production, and testing against it locally means that the developer is alerted quickly to a failure that will later occur on the build server, and is a fundamental, I guess, part of my personal mantra on this. So, what can we do at each stage of the build pipeline? We want to control our base images. The images on Docker Hub are trustable, we hope, after the recent breach. Docker does provide signing through the Notary service that we'll get to later, which negates most of these attacks against the image itself. Nevertheless, having an external dependency which will block a build time deployment if it goes down, like GitHub, like the Docker Hub, is not a nice story for anybody. So these should be denormalized. They should be copied into your organization's local Docker image registry to insulate from problems on the internet at large. Then they can be subjected to the organization's internal compliance and policy checkpoints. And of course, they can be rescanned for CVEs on a regular basis. The fact that we have immutable deployment artifacts means that what is in production is also exactly the same artifact as is sitting on our image registry server. So if we have a manifest of everything that is deployed into production via something declarative like GitOps, for example, of which I'm a huge proponent, then we can take the manifest of deployed images and scan them all offline. And we have to do that with regularity because, of course, an image version may have a CVE that languishes like Shellshock did for 20 years or so. And the day that that gets released, the CVE is published. We can perform that CVE correlation against the image and the file system. We know that we then have something in production that needs remediation. And the hardest job in security, which is hanging together attack chains and understanding whether a CVE actually has any has any impact, can be assessed, and we can make decisions as to what we actually deploy, whether we stop all the pipelines, etc. So we insulate ourselves from upstream availability changes or compromise. Hash-based addressing. This is the immutable nature of container artifacts. As I say, it's immutability via a slightly different angle, because instead of just saying, well, everything is immutable, we can't write to these file systems. Instead, we're saying we guarantee that this hash is exactly what you think it is, based upon the cryptographic hashing of the whole contents of the image. And then at runtime, there is this read-write layer on top of the image, which can change. Of course, we can lock that down as well, but running fully immutable systems is very difficult. Applications need to do probably at a minimum, for some of them, writing a PID, writing local files. So the benefits of immutability are more about the usage. The security benefits, you can generally get around immutability because you need something mutable to write to. And yep, as I've said, tags are transitory. They are just pointers. They are a human readable label to a hash pointer, but there's no correlation between the hash and the label, and as such, they kind of mean nothing. They should be treated with the utmost of caution. So, what will we do at the code stage? Well, static analysis. This is pretty standard. Everybody knows about this. We should be running tooling in our IDEs, or developers should be running in their IDEs so that they're able to, again, detect policy or compliance failures that will be kicked back to them by the build server, reducing that cycle time. It's all standard DevOps terminology, just with a security slant. Static analysis, of course, standard AppSec. There really is very little change here. One of the interesting projects, there's a few more in this talk, from the New York University Cybersecurity Lab, led by Justin Kapos, is this Atoms of Confusion project. And an atom of confusion is a piece of code that does not do what it looks like. So that project is based in C. They're doing the same thing for Go and various other languages. It's really quite fascinating, also terrifying. We look forward to the general adoption of Rust, of course. So, moving on, dependency analysis. The immediate dependencies, which are what we pull into our application, and our transitive dependencies, which is what is pulled in by that immediate dependency, which may be completely opaque to us. We don't necessarily know or care what is required for our immediate dependency to run. We just want it to fulfill the contract that we have with it. So, that being said, from a security perspective, and a provenance perspective, we do want to know exactly what those things are, but this is difficult and it's not often done. So, what else do we want? Hermetic, reproducible, and rootless builds. If anybody is at KubeCon, I'm doing another talk on this topic in some depth, going through the current state of build tooling. But suffice to say, we do not want inter-build data or artifact leakage. What does that mean? That means if you're sharing the Docker socket on a build server, any build can access all the other cache layers that have been written onto that server. So, do you trust your projects? How are they separated at deploy time? Is your organization big enough to start worrying about internal actors? These are the questions that are essentially negated by just preventing builds from being able to talk to each other's cache layers. Of course, the nuclear option is just to rely on a cloud provider. Google Cloud Build, for example, will just build from scratch every time. You can also do various things. I would recommend essentially using something like Canico at this point, because Docker Build by itself has various other compromises, although the latest version of BuildKit is really quite excellent, and yeah, we'll get onto this. Caching those build dependencies, there is also, Docker now supports referencing an image from which to pull the cache layers. So at build time, we can pull another image and use that as our local cache instead of relying upon layers that were left on the file system. Definitely, again, recommended. Reproducible builds. Pinning versions for deterministic builds is difficult and it is annoying. When an operating system repository package maintainer updates the version of one of those packages, they will often remove the previous version, which means if we've pinned our dependencies, our builds will just break. Now, there is a judgment call here to make, again, on a sort of per organization basis, which is, do I care more about knowing exactly what's in my images and manually bumping those versions, or do I care more about the developer productivity, things flowing through? Depends on your organization. Suffice to say, some consideration needs to be made here. Silently upgrading dependencies all the time is relatively nice. We obviously mitigate a lot of security threats by running against a more recent version, but running against the bleeding edge is more likely to affect system stability. Again, depending on what we're doing. This varies between Debian stable and Golang pulling head from GitHub. And there's a huge variance in between. All dependent, once again, on the risk posture. And finally, rootless builds. Building without privileged access. And in this case, privileged means root. So Docker has been heavily criticized over the years for running a root full daemon with no way to, with no eject button. This has historically been because of the lack of user namespaces. User namespaces transcend all other areas of the kernel. Version 1 was very difficult. It took a long time to get implemented, and it didn't quite work properly. If you enable user namespaces, it's disabled by default in Docker and Kubernetes. If you enable user namespaces, many of the images on Docker Hub will break. There are various things required to get them working. Happily, there are now thanks to some work by the LXC devs, there is now the shiftfs file system patch set hitting the kernel, which, just to rewind ever so slightly, the important point here is that in Linux, everything is a file, and every file has to be owned by somebody. So discretionary access control, which is how we integrate security into Linux at the very bottom level, is dependent upon the ownership of files or everything. So user namespaces transcend everything. It was very difficult to get this working because there are so many touch points across the kernel where user namespaces have to make policy or authorization decisions. So what the LXC guys have done is resurrect an old patch set called shiftfs, which essentially operates as a shim between multiple mount points for the same files from the host. So a read on that mount point is the user table is shifted by shiftfs instead of the kernel making those decisions. There are still some hacks in there, but it's been 3 years in the baking, more or less, and it's excellent that we're moving forward because these are very difficult problems to solve. So just moving on here, tools like Umochi, Image, Builder, and Kaneko give us a much safer, isolated, rootless build environment than we had before. Specifically, a lot of the work going on by the Docker build kit team has just permeated through. And yes, it's important to note that this class of build time attacks is generally more aspirational than in the wild, although, as we see, there are still mad CVEs that get dropped all the time. The run-C write over yourself with a symlink bug that came in this year caused a lot of problems. So, now that we've built the image, we want to verify that it meets our security best practice. So first, we must scan for vulnerabilities. Image scanning comes under criticism from some security guys because it is not a panacea, requires multiple things, especially the upstream CVE database to be well correlated with the files on disk. It's not an easy problem to solve, but minimum viable security, if you're doing nothing else, this will stop you shipping obvious CVEs to production. Next, we can scan for various configurations. So secrets in code. This really should be a second check after something in your build process that is initially scanning your Git repo. We shouldn't be able to get secrets this far through, but potentially someone's changed the Jenkins file or the Travis build to write a secret into the Docker file itself. So once we have the Docker immutable artifact, that needs scanning for various things. Images running as root, because the Docker daemon is running as root, when we have no user namespaces and the root user inside the container, that is the root user on the host. Check PS when you're running. Now, that is gated by various Linux security mechanisms. It's gated by various container security mechanisms. A huge amount of system calls are blocked with SE Linux. With the seccomp. SE Linux and AppArmor also have their own configurations on top of this. But ultimately, running images as root is a glorious way for a compromised container to then go and, if it can access it, remount the host file system. So we're still depending on discretionary access control for the host inside the container. And finally, misconfigurations. We probably don't want to have unauthenticated ports open, this kind of thing. Actually doing that statically is more difficult, so that would be looking at the port directive in the Docker file, for example. And then finally, policy. We don't want any critical vulnerabilities, for example. SUID and GUID binaries, again, Docker and containers are just Linux. So having set user ID binaries that allow you, that if they're misconfigured, can allow you to run things as root inside the container, it's still a problem, it's still just Linux. However, now we have a far more granular application of policy because we're only running one process per container. And that means that we can constrain what that process does in a particularly restrictive manner, as opposed to the monolithic deployment style, where our security policies for the whole VM have to encompass all the potential behaviors of the processes on that VM. So, we have followed all these best practices. The list is long, and we're at deployment time. We want to push an image to, in this case, production on Kubernetes. Because we have the guaranteed immutability of the image's hash, we can capture the metadata in the pipeline and associate it with that version of the image. Now, this is super powerful and broadly what the rest of the talk will be about. So, we've associated the metadata, we know what that image has done and what policy and compliance checks it has passed. We can now, at deployment time to the cluster, validate those steps. So if somebody is trying to use a break class procedure, they will also have to disable these policy checks that are performed inside the cluster on entry of new images. This is super powerful because it gives us another regulatory step, essentially, to prevent people, especially insiders in this case, from bypassing the policy and controls that we've placed on our pipelines. So this can validate not only that previous steps have passed, but also have not been circumvented, and that a malicious user with write access to the Kubernetes API is not deploying arbitrary code or arbitrary attack images. The simplest thing to do here is just to guarantee that all images, just to check rather, all images come from a registry that we control. And that registry might be production.acme.org. We're then checking various things, for example, that somebody is able to push to that image in the first place and then deploy from it secondarily. These are all just raising the bar that an attacker must overcome in order to attack the system. And finally, runtime configuration. It's all very well to configure these images correctly at build time, but if they're misconfigured at deployment time, then we can still have problems. Simply adding the privileged flag to a container disables AppArmor, seccomp, most of the user namespaces, gives access to the devices that are running on devices that exist on the host. It is a horrendous story. You can attack the host in many different ways at that point. It is probably the worst named and most dangerous flag in the history of computing, and ideally nothing ever should be privileged. It's giving a huge capability and feature set, and really if you just need network privilege, then just give capnet admin and deal with it that way instead of what is essentially, rooting your host. Pod security policy is just static analysis to ensure that the configuration of something that's deployed to a cluster is correct. And control plane have their own tool in the space called kubesec.io, which is static analysis for the deployment artifacts going into a cluster, along with recommendations. It gives you a risk score. I've actually been beavering away, and that will be open sourced at KubeCon, I hope, next week, which allows you to apply a more granular level of pod security policy. So, altogether, we have seen running containerized microservices leads to a fundamentally different security model than for virtual machines. And to summarize our best practices, we want to control our base images, we perform static analysis on our code, We then have a constrained and safe build environment for that code. Something else that's rarely considered here is the network that builds in. If somebody is able to drop a script into your Docker file, they can then, for example, scan the infrastructure that your container is building in. Then once we have that image, we can verify that what's been pulled in at build time or what came from the base image is still to our satisfaction in some way. And finally, we deploy, re-verifying all the previous steps and ensuring that everything did come out of the pipeline correctly. There is a lot to get done here. And frankly, only enterprises with sufficiently large teams generally check all of these boxes. And probably no organization is doing all of these things correctly, except maybe Shopify. So, in practice, how do we implement these and what tools should we use? Now, a lot of this tooling is still under active development, which is a good thing. Let's process through some detail. We will go into all of these in detail. So, a registry is required to hold our base images. The Docker Hub is one such registry. However, it no longer runs vulnerability scanning. There's always some discussion over Alpine or Ubuntu, Debian, based base images. Whatever you use, just make it consistent across the organization, because Docker will share file system at rest and at runtime, and memory and file system at runtime for these images when they're deployed on the same host. Everything's immutable, everything in memory is copy on write, so you can have 10 instances of the same container using the same memory space for the shared operating system code and whatever's running there, as well as the shared base image, and then what changes are these very thin write layers on top, plus whatever memory the application is using in its own allocated memory segment. Ensure you have proper access control and key rotation over the Docker Hub, and voila, a few weeks ago, that was called into play for everybody. Hopefully that is well automated and is able to spider out across your infrastructure. For example, automatically rotating keys in your build infrastructure. Code updates. There are two major players in this space, and they're tightly related. The update framework and Notary are both CNCF packages. The update framework is the specification. Notary is an implementation. What this does is it uses GPG to guarantee the freshness and the veracity and provenance of an image. So it will sign metadata about the image based on the hash. You will gather that via a side channel and then re-verify it when you've pulled the image. This protects us from upstream attacks like the Docker Hub. Docker has Notary running for its images, so we can be sure that they're not compromised, because that would also require a compromise of the GPG keys that are used for Notary, and they are deep. There are up to, I think there are up to 7 keys that you can use, and the point there is to prevent the loss of a single key compromising the entire infrastructure. It looks a lot like the global certificate root of trust for for TLS certificates. So the update, as we see, updates delegated by the root key. We have expiration on these things, so there is only a 30-day window in which a signed image can be pulled. That is configurable, but the point there is to prevent replay attacks. If I trust anything that's come from this registry, and this version was vulnerable, and we have deployed 100 times since then, well, if that's over a month ago, a man in the middle cannot inject that vulnerable version and force us to essentially downgrade our application to a vulnerable version. It's resistant to replay. It really is a wonderful and very interesting piece of software. This again is from Justin Kapos and Powell's, and there are lots of papers about this. Notary is the implementation of TUF that the Docker Hub uses, and as you can see, the best practices are to keep the root key offline. That probably means print it out or in a safe somewhere or in 2 places, one of them hopefully a salt mine. And we have trust delegation, which allows us to rotate keys very easily without worrying about redistributing them. Pipeline metadata. This is based upon the fact that we have this immutable hash for every container image. And we can attach events that have occurred, such as scanning. We can attach metadata about that to the image hash itself. There are a lot of things, a lot of events and data generated in the pipeline, and we can use this for audit and policy enforcement. Should we allow builds that depend upon vulnerable components, untested code, come from untrusted sources, are of unknown provenance? Generally we do. This gives us an opportunity to decide what our organization would like to do. Grafeas is an open source implementation of something Google have internally, which is, again, using this immutable artifact identifier and hanging off image scanning information about it. Now, it's gone through multiple sort of morphs and changes, but the project is still under active development. It is just a structured metadata API, essentially, and it integrates with various other things. The real benefit of this is that all metadata is in one place. We don't have some in our registry, some in our image scanning tool, some in our pipelines, some in the Git repo itself. We centralize it, we enforce policy, and we give that to security to make decisions or to report back. The Grafeas, this is all a bit deep, so I think I'll leave this here for posterity, but this is some of the depth on how Grafeas actually works. In reality, attestations are the commonality between all these tools, and mostly what Grafeas is now used for, because you can attest to anything. An attestation is a point in time, GPG signed checkbox saying this thing is this thing. So my image is missing any CVEs, or my image has passed my QA step, or something like this. So we can attest to arbitrary events, we can attest to things in our pipeline that we desire. That is the meat of it. In-toto is the same concept, but deployed differently. So it's a framework to provide software supply chain security and provides tooling and a metadata format, as you can see here, to ensure that all steps are performed sequentially and contain the correct inputs and outputs. So whereas Grafeas will attest to something arbitrary that it's told, in-toto will attest that the inputs and outputs of a step match a set of filters or requirements, and that the individual that undertook those steps is somebody that's permitted to do so, and that those steps occurred in some arbitrary order. It is ultimately the same idea, but implemented differently and separately. This is an example of an in-toto layout, and you can see, in this case, we only want somebody to git clone our demo project, and we expect this foo.py to have been generated by whatever build step we're doing. There are various other concepts. Again, there's a lot of depth in here that I won't go into, but I'll leave for posterity. And ultimately, we don't care what we're doing. We only care that whatever it is matches our layout, our specification for our events that are occurring. And those events generally build stages, but can be anything. There's also an emission controller for this, which is still under development. But it means, again, that we enforce all these things in our pipeline, and then we demand that when they're deployed to production, they are re-verified. So increasing the complexity of the system, but also the cost to an attacker. This is broadly how we describe things. Grafeas is on Rails, in-toto is unstructured. So in-toto can be used for frankly anything. It's been adopted by the reproducible builds project. So if you use Debian, then your builds are all run through in-toto. They are signed. The magic here is if somebody compromises one of the hundreds of build servers that build Debian packages, and the problem with trusting trust, they manipulate the compiler to output vulnerable or backdoored packages, then in-toto can say, well, look, I've had all these signed results and all these signed hashes from across the world, but these ones over here do not match. And then we say, okay, we've got reproducible builds that are guaranteed to produce bit for bit identical binary artifacts from the same build. So they don't have things in them like the time, they have no local entropy requirements because they don't need any entropy, they're doing something reproducible, and then they can be signed. The only thing that can possibly be different is, if they come from the same source, is the tooling that builds them. So this is really groundbreaking flavored stuff. Again, there's a lot to do, there's a lot of complexity, and the project is still under development, but very exciting. So, moving on to vulnerability scanning. I spoke about this briefly. We have these image layers that comprise an image, and then we have a thin read-write mutable layer on top that is custom per container. Image scanning tools will scan different things. Some will only scan the cumulative file system total of those 4 layers. Some will take each layer and scan them individually. My opinion is it's probably okay just to scan the cumulative final union of S layer, because if an attacker is able to get their hands and run the other layers, then you're probably in a worse position than it's probably a bad day at that point, let's say. So yeah, various different things, and the depth that these tools go to, so whether they just scan for operating system packages, which is what 90% of tools do, whether they care about your NPM, your Maven packages, whether they unbundle and extract compressed files, whether they check virus total for signatures, you get what you pay for essentially, and the difference between enterprise tooling and the free tooling is more or less that list there. There are 3 widely used open source scanners. This is probably a gross oversimplification, but Clair is, it's now under the IBM banner. It's CoreOS to IBM, CoreOS to Red Hat to IBM. Yes. Tool which will just scan for operating system packages. MVP, security, but it will not do anything more detailed. Anchore will do a little bit of, no it won't, sorry, Anchore will just do packages as well. Then we have Anchore, which has just released an enterprise version. The core of that is open source. Anchore has a very detailed and granular policy engine, which I rate quite highly. So yeah, from an open source perspective, you can have a look at those, and again, there are upsells involved, but some minimum level of scanning is required. Admission control. This is one of the best things about Kubernetes security. Instead of just authenticating and then authorizing a user, there is a third step. Authentication, authorization, admission control. So it's not just who are you and what resources are you using, it's finally, let's do a deep inspection on the resources that you're submitting. It's a wonderful, I'm deeply in favor, of course. What this means is that we can do 2 things during the admission control stage. We can mutate the inbound request, and then we can validate it. Of course, we mutate first, because if we've made a mistake there, the validation is twofold. First, for specification compliance, but secondarily, that's a good place to say, for example, are my images coming from a registry that I trust? They are extensible, which means that we can build and package our own and add them to the API server at runtime. And things like pod security policy are an internal admission controller anyway. Yes, so strongly recommended. There are, of course, other things in here. So the Notary and I skipped the name. The Portier. Sorry, we'll get to these. There are multiple admission controllers that are probably coming up on the next slide. Yeah, there we go. So Kritis is the admission controller for Grafeas. So this is taking all that pipeline metadata that's in Grafeas and calling out saying, this thing that someone submitted to me by an immutable hash, do you have a reference of it? And does it meet the criteria that I'm requesting? No CVEs, image policy, etc. Relatively simple. This actually exists in Google Cloud right now under the name binary authorization, which is the internal version that Google have open sourced. And you can see here there are whitelists on the image, and we can set the severity of package, vulnerabilities. So yeah, this tooling is available in a hosted form. Portieris is Notary's admission controller. Again, I'll just whiz through these briefly. There we go, we're done. So, there we have it. That's some of the steps required for an idealized an idealized supply chain. So, we have the security chiefly across 5 elements: the base image, code, build, application, and deploy. Minimal images limit our surface of attack. We scan our code for potential security issues, complete a formal security review, and we understand our dependencies, meet whatever policy we define. We build our images in a hermetic and reproducible way in as secure a manner as possible to defend against attacks against the pipeline from, as we've seen, the difficulty of defending from these supply chain attacks. Then once built, we scan our application image for known vulnerabilities and configuration problems, and at deployment time, we enforce specific requirements, meaning that when inevitably people are putting malicious code into our pipelines, we have done as much as possible to reduce its impact. So that is the state of the ecosystem, what we have available to us today. And it's essentially, we're not shipping any known CVs to production, and we are hardening as much as possible. And with that, I'm at the end. Thank you very much.